When J.J. Thomson discovered the electron, he was conducting experiments in electricity. Likewise, when we discovered that there were other particles in the atom, it was while experimenting on things other than just atoms. Our studies of the inside of the atom, the center of the atom, begin with the discovery of X-rays, which was just a little bit before J.J. Thomson discovered the electrons. A man named Wilhelm Röntgen discovered X-rays, created the first X-ray machine, and took the first X-ray images. And in fact, his wife, who often assisted in the research, often the X-rays were of her, actually died from radiation from these X-rays. Now, a little bit later, a man named Becquerel discovered radioactivity. And the way it happened was by accident. Becquerel was trying to discover if there was a link between X-rays and the fact that certain substances that gave off X-rays would also glow when exposed to ultraviolet radiation. So I have here a glass candy dish that's made with uranium, and we know uranium is radioactive, at least now we know it. Uranium was actually used all the way back in the 1860s, well before we knew it was radioactive. And one thing that scientists knew is it did give off X-rays, but it also had an interesting property. When ultraviolet radiation hit it, it would glow. And Becquerel was trying to find if there was a link between the X-rays and this glowing. Turns out there's no link. The fact that these radioactive elements glowed under black light, under ultraviolet light, was a little bit coincidental. And it turns out the X-rays were connected to something else. He discovered that these elements not only had X-rays given off, they also had some particles that were given off. And he didn't know much about what these particles were. Now, then a little bit later comes a scientist named Ernest Rutherford. Ernest Rutherford didn't know what to name these particles, so he called them alpha particles and beta particles. What he knew about them was that alpha particles were positive and were kind of big and clunky. Beta particles were negative and they moved really fast, and they were very, very light. So since he didn't know what they were, he came up with an idea that beta particles were really high energy electrons, and that turned out to be true. The beta particles were electrons. The alpha particles, however, the alpha particles were a little more clunky, and he discovered they were positively charged. He later explained what he thought they were. His idea was wrong, but the ideas he learned were very important. He created an experiment called the gold foil experiment. And the first thing was, he took a small radioactive substance that gave off alpha particles, and he fired these alpha particles at a really thin, fragile piece of gold foil. So what he did was he took this thing that gives off alpha particles and shoots them at high energy. He then took gold foil and put it in front of it, and he wrapped a detecting screen all the way around. The detecting screen could be thought of like, sort of like a photographic plate, where wherever the alpha particles hit this detecting screen, they would sort of leave a glow. And he began firing these really high energy positive particles at the gold foil. Now this gold foil is fragile. It's the kind of stuff that if you're touching it, working with it, it falls apart. If you were to sneeze, it would fall apart. Heck, if you even look at it the wrong way, it's going to fall apart. It's a really fragile foil. And he fired these high energy alpha particles at it. And what happened shocked him, because he expected that gold foil to be blown apart into little pieces by these alpha particles. And what happened totally caught him off guard, because these alpha particles, most of them went right through the gold foil as if it weren't even there. Some of them, though, when they went through the gold foil, they were sort of deflected or bounced off at some sort of odd angle. Some of them when they hit the gold foil, bounced straight back. They didn't even go through it. They bounced right back off that fragile stuff. And some of them bounced back at an angle. Now, this really did surprise Rutherford. In fact, he said it's like firing howitzer shells, big artillery shells, at tissue paper and finding that they bounce off. What did he conclude from this experiment? He concluded that because the alpha particles were pretty small compared to the size of gold atoms, that atoms must be mostly empty space. And these alpha particles that were positively charged, they would zoom right through the empty space of the gold atoms. Occasionally, though, these positively charged particles would get a little too close to a nucleus. And they were positive. The nucleus of the atom is positive. He didn't know it existed yet, but he concluded that in the middle of the atom there was something positive, and when these positive particles zoomed too close to something positive, they were repelled back. Some of them went by really close and were repelled a lot. Some of the particles, in fact, would actually hit those positive things and bounce back. So his conclusion is that atoms are mostly empty space. The center of the atom, though, is positively charged because the center of the atom, which took up very little space, was able to deflect these alpha particles, which were positive. So most of these alpha particles were able to zoom right through the empty space in the gold atoms that we can't see. Some of the particles, though, were deflected, meaning they got too close to the nucleus of the atom, which was where the positive charge was, and since they were positive, they ended up getting shot back at an angle. And a few of them were very much deflected, which means that the positive alpha particles actually hit the positive center of the atom and bounced back. But because most of them went right through the empty space, his conclusion is the center of the atom is positive. The center of the atom is very much concentrated into a small space, so it's very dense. And last, the nucleus, very, very small. Okay. Okay, looking over the conclusions that Ernest Rutherford came up with, there's one thing missing. He was able to describe all of this about the atoms of the gold foil, but he actually set out trying to explain beta particles and alpha particles. He did figure out what the beta particles were, but the alpha particles he couldn't figure out. This was his last mystery. The alpha particles, he believed, were made up of 4 positive particles and 2 negative particles that offset some of the charge of the positives. In our terms, he basically said that a alpha particle is 2 electrons and 4 protons. The masses he couldn't quite figure out, and another scientist later did piece it together. Niels Bohr is a big topic of next chapter, but in 1913, not long after Rutherford, he was doing a little bit of experiments with hydrogen gas, and he created the planetary model of the atom, which is the model that most of us learn as youngsters in elementary school, and we draw pictures of atoms showing protons and neutrons in the center, in the nucleus, and electrons that orbit around them in nice, clean, neat, even paths. That this model of the atom isn't 100% right either. In next chapter we'll get into the modern view of atoms. But it does a great job of explaining a lot of things, even bonding of very simple atoms like carbon, like we learned in biology class. Now the Niels Bohr model shows that there's a nucleus in the middle, and the electrons have certain paths that they must be on. And actually, electrons can jump from path to path, but they must stay on a path. They can't go in between paths. All right, the last scientist we work into this chapter answered Rutherford's question. And by the way, there's a little bit of irony here. Ernest Rutherford was actually a student of J.J. Thomson. He helped work with J.J. Thomson on his experiments where he discovered electricity as a student. Then Ernest Rutherford became the teacher, and one of his students that helped him on the gold foil experiment, a man named James Chadwick, finally explained what Rutherford couldn't. And it was a long time. Rutherford's experiment was 1911. Chadwick was not until the 1930s. And Chadwick picked up from both J.J. Thomson and Ernest Rutherford's experiments. He was trying to study, again, cathode ray tubes, but he had an idea called anode rays. If cathode rays carry electricity from the negative side to the positive side in a cathode ray tube, is there something going in the reverse direction from the positive side to the negative? That's what Chadwick wanted to solve. What he discovered instead was what those alpha particles really were for sure. Turns out alpha particles were not 4 positively charged protons and 2 negatively charged electrons. What they actually were particles that we didn't know existed. 2 protons and 2 neutrons. Now if you're listening, I did skip a step. Ernest Rutherford didn't actually discover the protons, but he discovered the charge of the nucleus, the positives. So you could say that every positive charge he discovered was 1 proton. A later scientist actually proved that the protons were a particle associated with it. But Chadwick was able to explain that missing piece of the puzzle with Rutherford. Where was all that mass coming from, the alpha particles? It turns out that there is one last particle, the neutron, which has no charge, but it does have a mass to it, and the mass is almost the same as the mass of a proton. So that finally brings us to a close on that chapter, looking at atomic theory. I want you to go back through the notes packet I gave you, use the PowerPoints if you need to, and make sure you fill in on all of the questions on the scientists. In class, we'll review that worksheet, and we won't talk about each individual scientist, but we'll do a summary of everything, and you will have a quiz, a matching quiz on the scientists, so please begin studying the scientists, but also use our Google Classroom site and our website to play some of the review games on atomic theory, just to make sure you know the individual scientists. I'll see you in class after the break.